Welcome to Homework Lib.
So in this question, we are trying to calculate the pressure at absolute zero. So when a molecule is at absolute zero, its electron motion is going to exert a pressure at where it's a container, where the atom is contained. So this amount of pressure can be calculated by pressure equals negative derivative of E of the energy, total energy over volume. And the purpose of this question is it wants us to calculate what this energy is. So the first thing, let's first find out what E total is. So E total, one thing to note is that this is not the same as Fermi's energy. This is equal to 3n over 5 Fermi's energy, 0-point energy. So because 3 over 5, 0-point energy is the average energy of the entire thing at 0 degree. And then we want to plug in the equation for Fermi energy. 0-point Fermi energy is pi 4/3 h bar squared over 2m. And then we have n 2 over 3. But then n is equal to the total number over the volume. Because small n is like the number density. So if we replace small n, the number density, by the total number over the volume, and then we can combine this total number with this and over here. So if we organize it a little bit, it becomes 3 over 5, 3 2 over 3, pi 4 over 3, h bar squared over 2m times big N 5 over 3 and v negative 2 over 3. And then we can find the pressure by taking the derivative of this. Over E total, I'll just write E total. So we can see all of this will not change, it will remain the same. But the last volume, which is what the derivative is taking it will become negative 2 over 3 v negative 5 over 3. So now it becomes 5 over 3 as well, and n is 5 over 3. So we can put them together again, and we can put negative 2 over 3 to the front. The 3 will cancel, it will become negative 2 over 5. And the 2 will also cancel with this 2 in the denominator. So if we simplify this whole thing, it will become 3 2 over 3 pi 4 over 3 h bar 2 over 5m, and then n over v 5 over 3. And compared to this Fermi energy, we can see that we pretty much changed a lot of 2's into 5's. That's the only difference. But that gives a pressure at 0 point. And then this is for part A. This is where the derivation comes from. For part B, we want to evaluate this pressure for copper, which has a concentration of 8.45. So that's small n, 8.45 times 10 to the 28. Okay, so let's calculate it. P equals 3 to the 2 over 3 pi times 4 times 3 times 10 to the negative 34 jar second square over 5 times mass of electron is 9.1 times 10 to the negative 31 kilogram. And then the number density is directly given to us. Small n is 8.45 times 10 to the 28 per meter cube, and is 5 over 3. So this gives us a pressure of 3.81 times 10 to the 10 Pascal. And if you want to express it in terms of the atmospheric pressure, this is 3.76 times 10 to the 5th atmospheric pressure. And then part C asks us, if this pressure is extremely high, then why doesn't the electron in a piece of copper simply explode out of the metal? Well, it's right, this pressure is extremely large. It's like 10,000 times, 20,000 times. It's like 100,000 times the atmospheric pressure. But at the same time, we know that the electrons are held in metal by the attractive force, and that attractive force exerted by the copper ions will overcome this pressure and hold the electrons to them. And I know this is a lot of force, but remember that electron and atoms, they are insanely close. They are very close together. So R is very small, and when R is very small, the amount of force exerted on the electron is pretty large. So the electric force between the atom and the electron is preventing the electrons from leaving the metal and explode.